Okay, in this video we're going to look at graphing polynomials. So if we can graph them from a certain form, then it'll make sense as long as we can put them into this form. So the form that we're going to look at is factored form. First of all, we need to know what a polynomial is. So a polynomial is anything, so a polynomial function that is, any function that can be written in the form, say, f of x equals a0 plus a1x plus a2x squared plus a3x cubed plus all the way up to some finishing value here, a(n)x to the n. Now normally when we see them, when we know what it is, we write them in the opposite order. But in order to write it in its general form, we need to write it like this because we don't know where n ends. Okay, so n is an integer value. Okay, so n is, actually it's a natural number, so it's any value greater than 0. That's a whole number. So n is a natural number. And if we want to look at an example of something like this, well, let's look at, I don't know, how about 3x squared plus 2x minus 4. Let's call that f of x. So if you're looking at that, well, you can see that n in this case is 2. Okay, so see how we go in the opposite order when we're writing an actual one? a0 is 4. So this is the constant term, a0. Then an, well, is going to be, n is going to be 2. So in this case, n equals 2. And a0 equals negative 4. a1 equals 2. And a2 equals 3. So there's a2, coefficient of x squared. a1 is the coefficient of x, and so on. Okay, another quick example might be f of x equals 3x to the 7 minus 4x cubed plus 2x minus 1. So in this case, this is a degree 7 polynomial. And so n equals 7 here. And so then a0 equals negative 1. a1 equals 2. a2 equals, well, there is no x squared term in here, so it must be 0. a3 equals negative 4. a4, 5, and 6 are not in this polynomial, so they equal 0. a4, a5, and a6 all equal 0. And then a7, which is the leading coefficient, equals 3. And we'll often refer to the leading coefficient as just a in the future. Okay, so these are polynomials. Now anything that can be written in this form is a polynomial. So for another example, f of x equal to 2x minus 3 times x plus 4. Can that be written in this form? Well, sure, you just expand it out. You get 2x squared minus 3x plus 8x, which will give us plus 5x, and then minus 12. Okay, so this can be written in this form. All right, what if I did another example of a polynomial that can be written in that form? How about f of x equals 2x minus 3, x plus 4. So it's the same as this one, and I'm going to add another factor. Another factor would be, let's say, x minus 1. Okay, so we know what this multiplies to. it's right there. So I'm going to replace that here, 2x squared plus 5x minus 12 times x minus 1. Okay? Now if we keep expanding here, we're going to get 2x squared times x. So that's going to be 2x cubed. Then 2x squared times negative 1 minus 2x squared. Then do this one times each one of them. So keep distributing each one in. So it's going to be plus 5x squared minus 5x minus 12x plus 12. Now collecting like terms, okay, you get 2x cubed plus 3x squared minus 17x plus 12. Now, this is a polynomial. X cubed, x squared, x, and a constant term. The A3 value is 2, A2 is 3, A1 is negative 17, and A0 is 12. So, basically you have three terms here with an x in each one. You multiply it out, you're going to get a cubic. This is a quadratic. If I had a fourth term, I'd have a quartic. If I had a fifth factor, I'd have a quintic. If I had a sixth factor and I multiply it out, I'd have a degree 6, degree 7, and so on polynomial. So I can write polynomials in this form, factored form. We just don't necessarily know how to go from this form here, the expanded form, to the factored form yet, but we will in a bit. We do know how to do it for quadratics, if it's possible, but we don't necessarily know how to do it for cubics or quartics and so on, but we will develop a method in the future. Okay, so we've got this. Now, to graph these, well, let's go to look at quadratics, and we'll look at the graphing part here. We know how to graph quadratics already, so we're just going to highlight what we know about it. So to graph, let's try f of x equals x minus 3 and x plus 4. So what we know about this in factored form is that we have two of the x-intercepts, right? So the zeros are x equals 3 and negative 4. Okay? We know it opens up because the a value is positive. So 3, so negative 4 and 3, and it's a parabola that goes like this. Okay? And we also know that the vertex is over here somewhere. But we can figure out the y-intercept. The y-intercept happens when x equals 0. So when you put x equal to 0 in there, y equals negative 3 times positive 4, which is negative 12. Okay, so that's negative 12 there. X, y on the axes, and we've got that. Okay. Now, what about another example here? Let's do a basic function f of x equals x cubed. Well, we should remember what this one looks like. If you don't, it's like this. When you cube positive numbers, they just get bigger, just like a quadratic, just faster. But when you cube negative numbers, they get bigger as well, but bigger negative, because when you cube a negative, it stays negative. So instead of going up like this, like a parabola, it comes down like this. Okay, so that's x cubed. And you can see that the end behaviors just go off to infinity and negative infinity. If I was to do x to the fourth, then when you put negative values to the power 4, it would look like a parabola again, but only sharper. To the exponent 5, well, it would do this again, because anything to the exponent 5 that's negative would stay negative, go down. So this is the type of graph that you'd have whenever the exponent is odd. The parabola y equals x squared is the type of graph you'd have whenever the exponent is even. Okay, at least at the ends. Sometimes it might go down and do other weird stuff. And we'll take a look at that. So let's take a look at a more complicated cubic. Let's say f of x equals x minus 4, x minus 1, and x plus 3. Well, to find the x-intercepts, we do just like we did with the quadratic up here. What values of x make y 0? Okay, at the x-intercepts, the y value is 0. So you're trying to solve for the values of x that make y 0. So in this case, the values of x that make y 0 here are x equal to 4 makes this whole thing 0. 4 minus 4 is 0. 0 times anything is 0. So 4, negative 1, or sorry, positive 1, and negative 3. So now we have the x-intercepts. Because the a value here, the a3 value actually, is positive. When you multiply this all out, you're going to get x cubed, 1x cubed. Because that is positive, it's going to behave like this one on the ends. So whenever the leading coefficient is positive, the right side always goes up. So when we go to graph this, okay, then we're going to plot the x-intercepts. So 4, 1, and negative 3. And we're going to start like this. We're going to go through, back, through, down. So the ends of this look like this cubic. Okay, the ends go in the same direction. But the middle is a little bit more complicated because of the x-intercepts. So it has to go through and down. Okay, and that's how we're going to graph polynomials. And there's going to be, so I'm going to give more examples of these graphs in another video of quartics and quintics and so on.